So let's take a look at a specific example using drilling mud to stabilize a bore well. So this example comes from petroleum engineering. When you drill down into the earth, uh, you drill deep enough, you're trying to reach some kind of oil reservoir beneath the surface of the earth, and they're usually quite deep. But what happens is that as the pressure builds up due to the oil inside this bore well, it can collapse the bore well. So what's done is you mix up a drilling fluid, which is called drilling mud, uh, and you adjust the density such that the pressure at A becomes zero. So let's say before we're drilling this oil well, we calculate that at 5 kilometers, uh, you know we know what the pressure up here is going to be 25 million pascals. Uh, we're going to pump the drilling mud down into the pipe to displace this oil and balance this pressure. So let's say the density of the oil, which we can look that up in a table. Uh, in this example, I'm giving it to you, but you can look on the internet or a lot of appendices. Let's say it's 880 kilograms per cubic meter. What should the density of the mud that we mix up be so that when we pump it down inside the well, the pressure at A becomes zero? So in order to work this problem, let's label the top of the well point A and the bottom of the well point B. So in this particular problem, we're given the following information. We know the depth of the well, which is 5,000 meters. We know the pressure at A, 25 times 10 to the 6 pascals, and we know the density of the oil um, that's given in the problem. Now, what we want the pressure at B without the mud is going to be equal to the pressure at A plus rho GH, where rho is the density of the oil. So if you calculate this, you get 68.164 times 10 to the 6 pascals. That's what the pressure at B would be without having the mud drilling mud in. So now let's pump in the drilling mud, and we want to pump in the drilling mud with a density such that the pressure at A is equal to zero. So the pressure at B is still going to be equal to the pressure at A plus, but now the oil is going to be replaced by the drilling mud. So the pressure of the mud uh, is simply rho mud GH, and the pressure at A, we want that to be zero up at the top. So this is zero, so you're left with the density of the mud times G times H is equal to the pressure at B, so you can solve for the density of the mud. You get the pressure divided by GH. So you can plug this in, calculate, you get 1,290 kilograms per cubic meter. That has to be the density of the mud in order that the pressure at A be zero.